Hello, everyone. Good afternoon. Welcome, welcome, welcome. Hope you're all doing super well and getting through the last little part of this semester. Why did it stop it? Okay. Let's see. We are in the middle of the actually, we're right at the end of the electrochemistry chapter, which we'll finish today. And then we'll start on looking at radioactivity. And that will probably be the last chapter we cover is radioactivity. So we're almost done, folks. Let's see. Do you guys have any questions for me before we get going? Sounds like you're growing some crystals, some alum crystals. Hopefully that's going well. Megan?
I have a question regarding the example we were doing yesterday. Yeah, it was like one of the last examples we did, and then it was similar to the post-lecture assignment.
This one?
How come? Yeah. How come you don't? Because the one in post-lecture, I can't remember off the top of my head, but one side had 2 electrons, but then the other side only had 1, but then you'd have to multiply everything by 2, right? So how come you don't multiply the voltage?
Oh, right. Because remember, the voltage is like a density, right? It's like a density. So if you have twice as much lead, do you multiply its density by 2 for the density of twice as much lead? No.
The density. Same.
So
Okay.
that in that way, the tables of half cell potentials are different from the tables of, let's say, enthalpies or entropies or free energies, right? Because those tables, if you multiply the equation by 2, you multiply the entropy by 2 or the enthalpy by 2, right? But for cell potentials, you don't. And that's because cell potentials are intensive. They're independent of the amount of material, okay? So they're kind of more like density.
Okay.
Okay. So it's absolutely right. You don't multiply it. You never multiply these by some factor to figure out each cell. Okay. All right, good. I'm glad you guys are helping each other here with the lab. Are there any other questions before we get going? Okay. Yeah, there's a question about chapter 26. I don't think we're going to do chapter 26. There's 1 day allotted for it on the syllabus, and that material is not super critical. It's kind of optional. If we had extra time, I'd probably get to it and maybe cover it a little bit. We'll see if I just give it a little bit of a glancing cover, but it won't be on the exam. Okay, I might cover it a little bit just for funs, but we'll see how we're doing. Okay, any other questions? All right, let's jump in here to electrochemistry. So we've looked at electrochemical cells, and what I want to talk about a little bit right now is batteries. And batteries are really just kind of nicely packaged electrochemical cells. Okay, so here's your typical, when you buy like a Duracell battery, right? It's something like this, and it has, like every electrochemical cell, it has 2 half reactions. The anode, or the oxidation, is zinc, oxidizing to zinc 2+. All right. The cathode is a graphite rod right here, but the graphite rod is just the medium for electrons to transfer through. The actual reaction is the reduction of manganese 4 oxide. So manganese 4 oxide reacts with the ammonium ion, right, to form ammonium hydroxide. And in this compound, and if you look at these half reactions and you add up the voltages, this has a voltage of 1.5 volts, right? So the most you can get out of this battery is 1.5 volts. But if you put them together in series, right, then you can add those voltages together, right? So if you have 2 of them, you get 3 volts. If you have 4 of them, you get 6 volts, and so on. Okay. These are not rechargeable, all right? But they are extremely useful, and we use them all the time. Alkaline dry cell is just a little bit of an upgrade from the acidic dry cell, usually a little more expensive. The only difference is that it runs in an alkaline environment, which is basic instead of acidic. And that allows the battery to have a longer shelf life. So now almost all the batteries we normally buy are these kind of alkaline. It's again, zinc is oxidized via this half reaction. Manganese 4 oxide is reduced, and you get a cell voltage of about 1.54 volts. Okay. Your car battery is actually a series of 6 electrochemical cells that are all wired in series and then put together as one battery. But within them, there's actually 6. Each one is about 2 volts, right? So your car battery overall is about 12 volts, right? The anode is the oxidation of lead to lead sulfate. The cathode is the reduction of lead 4 oxide, right? And what happens is that as these reactions occur, you form a lot of lead sulfate on these plates. And of course, if you just run it and run it and run it, eventually it'll die because you have coated all those plates with lead sulfate. But if you run the current backwards, right, these reactions run in reverse, and you regenerate the lead and the lead 4 oxide, right? So that's why it's reversible. This is a reversible reaction. When it runs in the forward direction, the spontaneous direction, it produces electricity, right? But in your car, you have something called an alternator, which can generate electricity and transfer it to the battery, and it causes the current to run in reverse, and that refreshes the reactants and gets rid of the products, and then the battery can produce electricity again. I don't know if V12 cars really have different batteries, do they? I think they have the same thing. I'm not sure about that, but I don't think the number of cylinders matters for this type of battery. I think motorcycles have a smaller version of this that only has 6 volts, and I think it's only 3 of them in series instead of 6 of them in series. Okay, so I don't really expect you to know anything about these batteries. I just wanted to kind of point them out and show you how these electrochemical cells that we've been talking about, right, are used around us all the time. Okay. All right, so far we've been talking about electrochemical cells that are spontaneous, right? That is, that they generate electricity, but we could also have electrochemical cells that require electricity in order to do what we want them to do. And those are called electrolytic cells. So for example, here is an electrochemical cell that we've been looking at quite a bit, zinc going to zinc 2+ and copper 2+ going to copper, right? We know that produces 1.10 volts, okay? If we, instead of allowing this to run in the forward direction and hooking up a voltmeter here or whatever else, or a light bulb or whatever else we want, we put in a voltage source that is greater than 1.10 volts, and we hook it up such that the negative side is over here and the positive side is over here. Then what happens is that forces electrons to run in the reverse direction, okay? So electrons run from the negative terminal to here, to the zinc, and are attracted to the positive terminal of the battery. So what does that do? That makes these reactions run in reverse, okay? So here, instead of zinc being oxidized, zinc is reduced, and instead of copper 2+, instead of copper 2+ being reduced, copper 2+ is sorry, instead of copper 2 plus being reduced, copper is oxidized on over here, right? So it just makes both of these reactions run backwards, yeah? So what was the anode now becomes the cathode, and what was the cathode now becomes the anode, all right? Because anode is always where what occurs?
Oxidation.
Oxidation. Correct. Sophia, did you have a question?
I was just wanting to situate myself what would be like a lot of voltage, like in a house, for example. What's the normal voltage?
Oh,
Like
good question.
3?
Okay, so a house has 120 volts, but that's alternating current and not direct current. So all of these batteries that we're talking about all provide direct current, which means that the electrons just flow in one direction. Alternating current actually has electrons flowing back and forth really fast. And then usually the voltages are much higher. Okay, so, but just to get you calibrated, your car battery is 12 volts.
Okay.
Right, but in your house, what you plug into is 120 volts, so that's a lot more. But it's a different kind of electrical current. It's called alternating current instead of direct current.
Thank you.
All right, so what can you do with, why is this electrolysis useful? Well, and for batteries, right, it allows you to recharge the battery, right? So you run the battery down by letting it run in the forward direction, then you hook up to an external electricity source and you can recharge the battery, all right? So that's how rechargeable batteries basically work. You could also do interesting chemistry. So for example, you can break water up into hydrogen and oxygen using electrolysis, right? So this is a little electrolysis cell that shows these half reactions. This is what happens at the anode. Water is broken up to oxygen. At the cathode, water is broken up into hydrogen, right? And so essentially overall, when you add these together, you get water breaking up into hydrogen and oxygen, right? The spontaneous reaction is obviously in the other direction, hydrogen plus oxygen going to water. So this is not spontaneous, but you can use electrical current to do it. Why is this useful? Well, if hydrogen would be a great fuel, right? You can use hydrogen, you can burn it directly like they do in the space shuttle for propulsion, or you can put it in a hydrogen fuel cell. Hydrogen fuel cell is like a battery that where you replace the reactants and products continuously, okay? And so you can use, this is not a hydrogen fuel cell, but the hydrogen that you make this way could be used in a hydrogen fuel cell. Hydrogen fuel cell is the reverse of this. It combines hydrogen and oxygen in an electrochemical cell to produce water. And that process is spontaneous. Breaking it apart is not spontaneous, right? But imagine if you could do this with solar energy, right? Use solar energy, you could make hydrogen, and then your hydrogen is a fuel, you can run your car on that, right? So that's a possible future scenario for our energy needs. Right now, it's kind of expensive to do that, but all these technologies tend to go down in price over time, and eventually that might be the way we all get our energy. Electrolysis can be used for electroplating. So for example, if you want to coat silver onto some other metal, right, you can use an electrolytic cell to do that. So the anode and the cathode, notice here, are exactly the same reaction, just reverse, right? So E cell is 0, but if you provide an external voltage source, right, you can cause electrons to be drawn out of here and pushed down into here so that the silver coats on your cathode, right? So if you have some metal object that you want to silver plate, you can do that, put the silver on, and depending on how much current you run through this thing, it'll tell you how much silver gets deposited. All right, let's see. There's some questions. Wasn't there a car they invented with a hydrogen fuel cell? Yes, yeah, it is the Toyota Mirai. It was a Toyota Mirai, yeah. It's still being made. In fact, they updated it this year, and they have a new model that's looking pretty slick. You can look it up if you want. It's called the Toyota Mirai, M-I-R-A-I. It runs on hydrogen with a fuel cell. The problem with them at the moment is that there's not that many hydrogen fuel stations around. I think California has about 50 of them, you know, throughout California. I actually think that car is only sold in California because the rest of the country doesn't really have a bunch of hydrogen fuel stations. But we'll see. Definitely, cars are moving away from fossil fuels. That trend will continue. And whether they go towards battery operated, fully battery operated like the Tesla, or whether they go towards hydrogen fuel cells like the Mirai remains to be seen, right? We'll just have to wait and see. But there's a lot of technology out there that's replacing cars that run on gasoline, that's for sure. Okay. Yeah, maybe battery swap. Although the battery charging times keep getting lower and lower. I think there's some electric cars now that you can get 80% charge in like 20 minutes, something like that. So pretty interesting, right? Using the technology we're talking about in this chapter. All right, let me talk a little bit about, oh, I see a question, Taylor.
I said 2 questions. Can you go to the previous one, the previous slide? So you said like you can increase the current, and that tells you like how much how to say this, how much plating gets plated onto the object, you know?
Correct.
So it's not really like you can basically just have like a ton of voltage go through, and you can just put a ton if you want on there, or like a little slim coating.
Correct. You can control it by the amount of current, by how long you run the current for.
Okay.
Right?
Not the concentration.
Pardon me?
Sorry, not the concentration, or would that?
You need a certain amount of voltage to get this going, but then once it's going, what controls how much silver is plated is the current, right? Because every one electron coats one silver ion, right? So you actually have stoichiometry here, which I'll show you how to calculate that in a minute.
Oh, okay.
And
Okay.
yeah, this electroplating technique will work for other metals, absolutely.
Okay.
It's used to gold plate,
Cool.
like gold plated substances, for example, silver plating, copper plating, those all work in this way. Yep.
So it's kind of like a precipitation reaction, but it's powered by the current. Is that
Yeah,
you can kind of
you can kind of think of it that way.
Okay.
Yeah, it's not usually called a precipitation reaction, but it is in some ways it is like a precipitation reaction.
Okay. That's pretty interesting. All right.
Yeah,
Thank you.
it's really cool. You know, if we had real labs, we could do a lab where we do this and just coat some aluminum or coat some silver onto some other metal surface. It's kind of fun.
What's a real lab?
What'd you
Is
say?
that like an in-person thing? Like,
What's a real
is that where you,
lab?
like,
Yeah.
meet people? Yeah.
Yeah, exactly. That's like this thing where you actually go into this room and there's other people in there
Oh, what?
and they're not wearing masks. It's crazy.
Oh,
It'll come back. Keep getting your vaccines. That's what'll make it come back. All right. Good. All right. So how do we the stoichiometry of electrolysis can give us a relationship between the amount of current we pass and the amount of, let's say, reaction that happens, right? So in something like electroplating, the amount of metal deposited, right, is directly proportional to the charge and the current and the length of time. All right. So the charge that flows through the cell, remember that current, right? Remember the units is amps, right? And 1 amp is equal to 1 coulomb per second. Okay. And in addition to that, the charge of a mole of electrons is 96,485 coulombs. So 96,485 coulombs is the charge of 1 mole of electrons, right? So you can use both of these together to basically do the stoichiometry of electrolysis, all right? So let's just do this example. Let's calculate the mass of gold that can be plated in 25 minutes using 5.5 amps for this particular half reaction. So let's just set this up like we would normally set up our problems. We're given 25 minutes. We're given 5.5 amps. Can you guys hear me okay? And you're given this half reaction, which tells you that 1 mole of Au3 plus is proportional to 3 moles of electrons, right? This is a stoichiometric relationship, right? Between the moles of electrons and the moles of gold, right? So it's just like other stoichiometry that we've done in this class, right? Except we're dealing with figuring out how many moles of electrons, right? So we're given 25 minutes of 5.5 amps, and we want to find the mass of gold. The mass of gold that's plated, right? So this is just, you can follow the units on this one and work it like you were working a stoichiometry problem, right? We'd start out with the time, because we're wanting to figure out how many moles of electrons. So we got 25 minutes. We know the number, we know the amps, right? So remember, this is the same thing as 5.5 coulombs per second, right? So we need this in seconds instead of minutes, right? So we'll change that to minutes. Sorry, to seconds, from minutes to seconds. That'll cancel. And then we can multiply by 5.5 coulombs per second, right? And the seconds cancel. And then now we got to get from coulombs, which is a unit of charge, to moles of electrons, right? But we know that 1 mole of electrons has a charge of 96,485 coulombs, right? So we'll just do 96,485 coulombs per 1 mole of electrons, right? And now we get from coulombs to mole of electrons, right? And now we need a conversion between moles of electrons and moles of gold, right? What's that conversion based on the balanced equation?
3 to 1.
3 to 1, right? 3 moles of electrons, 1 mole of gold, right? And that gets us to moles of gold, right? If we want to get to grams, we need one more step. What's that?
The molar mass.
Yep, the molar mass, 196.97 grams per mole of gold, right? So that gets us to grams of gold. If you carry all that out, you'll find that you actually get 5.6 grams of gold. Okay. So, you know, the main part of this is this stoichiometric ratio here, which you can get from the half reaction. All right. And then the other important part is realizing that a coulomb per second, you can get to, if you have coulombs per second and you have time, you can get to moles of electrons, right? Does that make sense? Okay, cool. Good, good. All right, one last topic here, and we'll be finished with electrochemistry, and that topic is corrosion. So corrosion is, you know it probably most as rusting, right? If you leave iron things out over time in the weather, or especially in salt air, they'll tend to rust, right? So other metals, it's actually the oxidation of iron that you're seeing, and rust is a form of iron oxide, right? Other metals will also undergo this kind of spontaneous oxidation because we have an atmosphere that has oxygen in it, right? And oxygen is good at causing the oxidation of other things, right? Which is why it's ultimately called oxidation instead of electronification or something, or lose electronification or something like that, right? It's called oxidation because oxygen is very good at oxidizing other things. So many of them, many materials we use are metals, and corrosion can be a very big problem. You know, bridges get rusted out, cars get rusted out, our bikes get rusted. And so we want to try to stop corrosion. And there are some ways to stop it. We'll talk about those in a minute. But corrosion or rusting is a little bit of a complicated process. You don't really have to understand all of this nor memorize it or anything. But the main things are that you have iron going to Fe2+, all right? And that often happens where there's an irregularity in the surface. So if you notice, if you have a surface of iron and you get a little dent in it or something, or a chip, right, that'll expose it to this oxidation of iron, right? Oxygen gets reduced, right? And then there's a reaction between iron and oxygen in water that ends up forming Fe2O3.NH2O, this is what we normally call rust. This is that orange substance, right? So this is what's happening, you know, on your bike as it gets rusted out. You can prevent corrosion in a couple of ways. Notice that you need to have water present for corrosion to happen. And you also need the conduction of electricity, right? And so that's why salt sort of enhances corrosion, because salt makes the water more conductive. Sorry about that. Taylor, do you have a quick question?
Yeah. In the divot, like if you had a perfectly smooth surface, would it rust? Or
it could still rust, but what happens is
Okay.
that in the divot, the potential energy of the iron atoms goes up a little bit right there at that surface that's kind of rough. And because of that, it's more susceptible to rusting. So it'll usually start there.
Okay, that makes sense now.
Yeah.
So it's like the surface area
Yeah.
and also like,
exactly
okay,
right.
got it.
Yep.
Okay.
That
So it's
little
just like a weak,
irregularity will make that area a little more susceptible than a perfectly flat area.
okay, cool. Thank you.
So what can you do? You can coat the metal, right? So you can paint it. Like, for example, our cars are mostly made of steel, right? Which is an iron alloy. And the way we prevent them from rusting is by painting them, right? We put a coating on them, in that case, paint. You can also prevent rusting with something called a sacrificial electrode. And this is kind of interesting. So you might have some pipes, for example, that are underground. And of course, it's moist down there and susceptible to rust. But you can hook up an electrical circuit where you connect the pipe to what's called a sacrificial electrode. What's a sacrificial electrode? A sacrificial electrode is simply a metal that has a greater tendency to lose electrons than iron, right? So if you look here, right, here's the oxidation of iron right here, right? So if you hook up iron to something like magnesium, right, what happens? Magnesium oxidizes instead of the iron, right? And it would in fact cause the reduction of iron 3+. So remember, any reaction on this table is spontaneous in the forward direction when paired with the reverse of a reaction here, right? So let's say your iron tries to rust a little bit and the magnesium says, right? I want to get rid of my electrons more than you want to get rid of yours, right? So the magnesium throws its electrons at iron and forces it to not rust. Does that make sense? Right? In other words, you have iron and magnesium here. They both want to lose electrons, but who wants to lose the electrons more badly? Magnesium, right? Because it's lower on this list. So magnesium actually loses electrons and causes the reduction of iron and protects this pipe. And since this pipe conducts electricity and this wire conducts electricity, right, you can protect a lot of pipe with a little wire that goes up to the surface, and you put a piece of magnesium up there connected electrically. And then periodically you change out the magnesium, right? So you have an electrical contact with the magnesium, and then periodically it's going to oxidize away instead of the iron. And then you just take it out and put in a new piece of magnesium, and then you got another years of protection or whatever, however long it lasts, right? Pretty ingenious, right? It's kind of a cool, simple way to prevent rusting. I don't know, like how, I think it can protect quite a long ways of pipe, right? Because of the the current can run through the pipe. Eventually there's resistance and it falls off. So how often along a pipe you have to put these sacrificial electrodes would depend on the details of the pipe, right? How thick it is and how long it is. But anyway, this system works and it's often used to prevent rusting. All right, good. Any questions on the end of electrochemistry? Okay, I don't see any questions. So let's switch gears here.
Trey, I have just a question on when using the chart, the one
Yes.
you're just showing.
Yep.
Some equations don't appear, and I guess it would be in Appendix 2B. I've found some of them. But then my other question is, you know that is the equation you're looking for because it's the same amount of products, and then the electrons will depend. Like, for example, some of the chapter sets for this week was like, I don't know, magnesium or something, and then there's like magnesium O2, but then you just have to look at magnesium 2 plus depending on whatever is in the equation they're giving you, right?
Correct. You have to break up your overall equation into the half reactions, right, which are the oxidation and reduction, and then try to match them with the half reactions that are in the table.
Okay, so it's just a matter of looking at the table.
Yeah, it's just a matter of looking. Correct.
Yeah.
Yeah. Good question. Okay. So let's switch gears here and let's start talking a little bit about nuclear chemistry. All right. So so far we've been talking about atoms reacting with other atoms to form compounds, compounds reacting with other compounds, right? But we haven't really, and remember when we talked about Dalton's atomic theory, right? Dalton said that, look, atoms of one element can't change into atoms of another element, right? So carbon is always carbon and hydrogen is always hydrogen, right? But in fact, that was an oversimplification, okay? Atoms of one element can change to atoms of another element. How would that happen? Well, what defines an element? It's the particles in the nucleus, right? The number of protons in the nucleus. So for example, carbon has 6 protons, right? So if you change the number of protons in the nucleus of carbon, right, you would turn carbon into some other element, right? So those kinds of changes are what nuclear chemistry is about, okay? Changes within the nucleus of atoms, which we haven't talked about yet, all right? But we will in this chapter. So nuclear chemistry has some interesting applications. Do you know of any?
Nuclear power.
Nuclear power, right?
When they smash atoms together, I don't know what they call that.
So nuclear power is an interesting application of nuclear chemistry. Do you know, can you name a nuclear power plant?
San Onofre.
San Onofre, yeah. If you drive down to San Diego, right, along the 405, you'll pass the San Onofre power plant. And right in front of the San Onofre power plant is a great surf spot called the San Onofre. And people surf there all the time.
Fukushima?
Pardon me?
Fukushima?
Hiroshima?
No,
So-
Fukushima.
So in Hiroshima, that
No,
was
I said Fukushima.
Oh, Fukushima, yes. That was a nuclear power plant accident, right? That was caused by a tsunami, right? Chernobyl is another nuclear power plant accident that was caused by an experiment they were trying to do while operating the plant, and the experiment went bad, right? So nuclear power definitely is one big application of nuclear chemistry. What are some others?
Is radiocarbon dating
Yes.
application?
Yes. Radiocarbon dating, right? And
Um,
that has nothing to do with Tinder or anything like that, right? It's not a special dating app. It has to do with gauging or measuring the age of substances that were once alive, but then have since died and time has passed. So you can use nuclear chemistry to determine, for example, how old a particular skull is that you might have found as an archaeologist, right? Or how old certain scrolls that you found, right? So measuring the age of things, because nuclear chemistry provides sort of a natural clock, right? That you can use to measure how old things are. Nuclear medicine is another good one. I know some of you want to become, are interested in medicine, right? And want to eventually go to medical school and perhaps become a physician. So nuclear medicine is a very, very important application of nuclear chemistry. I'll tell you a quick story here. So one time, I don't know, probably it must have been about 20 years ago or so. It's been a while now, but I had kind of a pain on my lower right quadrant, right? In the lower bottom of my stomach, right? And a lot of you probably know what that's associated with, right? Anybody?
Appendicitis.
Appendicitis, yeah, appendicitis. So I thought I might have appendicitis. So I went to the emergency room, right? And so they sort of looked at me and said, yeah, it kind of seems like it's probably appendicitis. So appendicitis, what happens when you have appendicitis is you get an infection in your appendix, right? And the appendix, if unchecked, the appendix can burst, and then all that infection can spread. So it's the kind of thing that needs pretty immediate attention if you have appendicitis. Anyway, but because it's an infection, one way to kind of a general way to test for appendicitis is to give you test your blood for antibodies, right? Because if you have an infection, your body usually has an elevated level of antibodies, right? Trying to fight that infection. So a lot of times that's the first thing they'll do for people who come in and seem like they have appendicitis. They'll do a blood test and they see if you have elevated antibodies. Well, they did that test to me and no elevated antibodies, right? And I thought, oh, well, sometimes, you don't get that big an elevation in your antibodies. And so maybe we still think you have appendicitis. We could either just operate and take out your appendix. There's a chance it could be healthy. But that wouldn't hurt anything. And if it's infected, you definitely need to get it out. But they also said that they had another test they can do to double check. And that test involved nuclear medicine. And it kind of shows the kind of thing you could do with nuclear medicine. So here's what they do. They take antibodies and they tag them with something that is radioactive, okay? So a substance that's radioactive will emit particles. Okay, so one thing we'll learn about here as we learn about the different kinds of radioactivity is all the different kinds of radioactivity are atoms that have some instability associated with them that causes it to emit particles from its nucleus. Okay, and these particles have pretty high energy and are pretty easy to detect. All right, so what they do is they give you this antibody. They inject you with antibodies that are tagged with a radioactive substance, right? And then they wait a little while. You sit there for about half an hour, right? While those antibodies circle through your body, right? And what are they going to do? They're going to concentrate in any areas that have infection, right? So if you have an infection in your appendix, right, you'd have these antibodies gathering at your appendix. And of course, they're radioactive. So they're giving off these particles, right? So then they basically scan you to see if there are radioactive particles being emitted from your appendix, right? And so that's what they did. And again, negative, right? So they just sent me home. And the next day I felt better. And I still have my appendix. So nuclear medicine saved me from surgery, I guess, even though it wasn't too bad of it's not too bad of a surgery if you have to have it. Okay. There's some other questions here. Let me see in the chat. You can make new elements, yeah, by that. In fact, yeah, they do that in Berkeley. In fact, there's an element called berkelium and another one called californium, both of them discovered at Berkeley. And what you basically do is you take small atoms and you smash them together so hard that their nuclei can join, right? Or you take a big atom and you throw a proton in there or a neutron in there so that it can join, and then you get bigger atoms, right? A lot of these are normally pretty unstable though. What else? Oh, yeah, I think those are the main questions. Okay, so nuclear power, radiocarbon dating, nuclear medicine, still missing one big one.
Nuclear weapons.
Nuclear weapons, right. So two major type of nuclear weapons. The first ones were atomic bombs, right? And atomic bombs were what we dropped on Hiroshima and Nagasaki during the end of World War II, right? And then hydrogen bombs, which are about 1,000 times more powerful than that, right? Atomic bombs use nuclear fission. Fission is taking a big atom and breaking it into smaller ones. Hydrogen bombs use nuclear fusion, which is taking two smaller atoms and fusing them into a bigger one. Okay, so that's the difference between fission and fusion. So we'll talk about all this throughout this chapter, but these are some of the applications of nuclear chemistry, and they're super interesting. Some of them, of course, are controversial. Nuclear power. We're not using as much nuclear power as we used to, especially after Fukushima and Chernobyl accidents, although nuclear power is a fossil fuel free type of power, right? So nuclear power doesn't contribute to global warming, for example, or climate change, but it does have some of its own issues, and all power sources really have issues. And the question is, which kind of issues do we want to deal with, right? Okay, so let's jump in here and we'll start talking about the discovery of radioactivity. So the discovery of radioactivity was made about in the late 1800s, right about the turn of the century. And there was a scientist by the name of Becquerel. His name was Antoine. Get the spelling right here. Becquerel. All right. And he was interested in sort of the newfound X-rays. So right about this time, scientists had discovered X-rays, and X-rays were like this magical thing, right? Because you could take pictures of people's bones in their hands, right? You could take pictures of coins through a door, right? All this crazy stuff that you couldn't do before. So X-rays were, when they first were discovered, were sort of a hot area of research. And Becquerel hypothesized that there was a connection between the emission of X-rays and phosphorescence. What's phosphorescence? Have you ever seen like those little, like, sometimes college students will buy those glow in the dark stars and put them on the roof of their dorm room, right? It's just a way to entice other people to come in and turn off the lights, right? And because then they all glow, all the stars glow, right? That glow is phosphorescence. So what happens in phosphorescence is you have some sort of substance that you expose to light, right? And then you bring it, then it excites the atoms, it excites electrons in atoms, and then as the electrons relax back down, they emit light, and it's often kind of a greenish light, right? You guys all know what I'm talking about? So Becquerel thought there was a connection between that, right, phosphorescence, and the emission of X-rays. All right. So he wasn't trying to discover radioactivity. He didn't even know radioactivity existed, right? He was trying to make this connection between phosphorescence and X-rays. So you can see how sometimes in science, you discover things kind of by accident. This was one of those accidents. All right. So what he did is he had these crystals that phosphoresced, right? Imagine he had a few of those phosphorescent stars, all right? But anyway, there were these crystals that phosphoresce. They happen to contain uranium in them, right? But that wasn't what he was studying. He was studying phosphorescence, and he thought, okay, there's a connection between phosphorescence and X-rays. So what he did is he took a photographic plate, right? He put his crystals on top of the plate, and then he wrapped the plate in a dark cloth, right? So that the plate could not be exposed by normal light, right? And then he took this out into the sunshine, right? And he let the crystals absorb sunlight, right? And get excited to upper states. And then he put the crystals on top of this photographic plate that was wrapped in this dark cloth, right? And he let them sit there for a while, okay? And he observed that they would, of course, glow the familiar green glow of phosphorescence, okay? But then what he did is he looked at the plates, right? And he saw what you see here in this image. These are actually the images that he took pictures of. You see these dark spots where the crystals were, right? Which means that the photographic plate was exposed, right? But it wasn't exposed by the phosphorescence, right? Because the phosphorescent was visible light, and the visible light couldn't get through the dark cloth, but X-rays could get through the dark cloth, right? So he thought, oh, okay, there's a connection. When something phosphoresces, it also emits X-rays, and that's what was causing this exposure, all right? But apparently, at least according to the story, Becquerel, there was, he repeated his experiment several times, but there were some days that were particularly cloudy and stormy. So instead of exposing his crystal, he didn't have enough sunlight to really expose the crystals to sunlight. So he threw them in his desk drawer in the dark on top of the photographic plate. And then he said, oh, what the heck? It's been gray for a week. I'm just going to see if the plate is exposed even without the sunlight, right? So in other words, what would the plate be exposed even without the crystals phosphorescing? Okay. And sure enough, he looked at the plates again, and even without the phosphorescence, they were exposed. Okay. So he was like, well, what the heck? So it turned out that these crystals would expose the plate no matter what, over and over again, right? So he said, okay, so something is being given off by these crystals. Well, it turns out it was the uranium in the crystals, right, that were giving off radioactive particles, okay? The uranium itself was radioactive, so he wouldn't have to do anything, and these crystals would expose the plate because they were radioactive, okay? So radioactivity is the emission of energetic particles from the nucleus of some unstable, or that's not a very good definition, there's not very good wording, but some unstable nuclei. Okay, the emission of radioactive particles from the nucleus of some unstable nuclei. Then I'm glad people are asking about Marie Curie, because she's next on the scene. She was a graduate student of Becquerel. Okay, and Becquerel had called these things uranic rays, right? Because what he discovered was that, of course, they came from the uranium, right? So he called them uranic rays. And Marie Curie came on the scene, and so emission of what particles? We'll get to the particles in a minute, okay? Just right now, think of them as things like protons, neutrons, electrons, photons. They're just energetic particles, and they're pieces of the nucleus, right? Is basically what they are. So she started looking to see if other things emitted such particles, right? And she discovered that, in fact, these rays were given off by many other things in addition to uranium, right? Which which caused their names to be changed. In fact, from uranic rays, it went to reactivity, which then later became radioactivity, right? But in the process, she also discovered some new elements. So there's a couple elements on the periodic table. One of them is called curium. It's named after her. But the ones she discovered were, let's see, what were they? They were, I have to look at periodic table here real quick. Let's see, she discovered, what was it? Radium, which is right here. And one other one. What was the other one? Do I have it here? I can't remember what the other one was. But anyway, she won the Nobel Prize in physics, first of all, with Becquerel for the discovery. Oh no, it was polonium. The other one she discovered was polonium. She named it polonium. Does anyone know why?
Poland.
She was from Poland. Yeah, she was from Poland. So radium, she named radium because it was so radioactive. It was way more radioactive than uranium. And then polonium, she named after her home country. So anyway, she shared the Nobel Prize with Becquerel for the discovery of radioactivity, right? And then she won a second Nobel Prize in chemistry. So she won a Nobel Prize in physics. Then she won a Nobel Prize in chemistry for the discovery of 2 new elements. And then her daughter, this daughter right here, became a nuclear physicist as well. She won a Nobel Prize. And her other daughter, Ava, didn't become a scientist. She became a writer and wrote a biography about the family, right? So it was a very amazing set of women that made big contributions to nuclear processes. Okay, so let's look at the different types of radioactivity, all right? And what are these particles that are being given off by these nuclear processes? So first, let me remind you about the notation that we use. I keep getting a signal that my internet's a little unstable. Can you guys hear me okay? Oh yeah, why is the radioactivity considered physics and not chem? Yeah, because the things that occur in the nucleus of atoms are typically part of nuclear physics, right? But they do overlap in the chemistry. So nuclear chemistry is, the study of the nucleus is kind of in between chemistry and physics. So how you characterize it, I don't know. But the discovery of radioactivity was at least the Nobel Prize was given in physics for that discovery. Okay, so we have to review this, which is the way we learned last semester that we can specify a nucleus, right? So for example, carbon 612 would be an example of this kind of nuclear notation, right? Remember, this is the atomic number. What does the atomic number tell you?
Number of protons.
Number of protons, right? And this is the mass number. And do you remember what the mass number tells you?
Protons plus neutrons.
Protons plus neutrons, right? So when we write carbon 612, we mean that there are 6 protons in the nucleus and then 6 neutrons as well for a total of 12, right? And remember that carbon, for example, has other isotopes, right? Like carbon 13. And this isotope, of course, has 6 protons because all carbon atoms have 6 protons, but it has 7 neutrons, right? And so that mass number up there tells you the sum of both of those, okay? So using this symbol, if we want to symbolize a proton can be symbolized like this, hydrogen 1, or it can be symbolized like this with a P symbol. A neutron can be symbolized like this, 0 charge but 1 mass, right? A proton, of course, has 1 charge and 1 mass. Or an electron is charge of -1 and 0 mass because it's so light compared to a neutron or a proton. Okay. An alpha particle is a helium nucleus. So helium nucleus is symbolized like this. A beta particle is just another way of another name for an electron, but an electron in the context of radioactivity. Okay, so in the context of radioactivity, we call an electron a beta particle. And then a positron, this is a particle we have not really encountered before in this class. And that is, it has the charge of an electron, it has the mass of an electron, sorry. And the magnitude of the charge is the same as the charge of an electron, but the sign is opposite. So it's like an electron with a positive charge, right? Yeah, you have to remember, you have to know, not all of these, but a lot of these you'll have to know because you have to be able to write nuclear equations. But we'll go through all of those here in just a minute. An electron and a positron, the positron is the antimatter of an electron. So you may have heard that term before. Antimatter is really the same in every way, but opposite in charge. And when an electron and a positron meet, they annihilate one another, right? So, you know, some theories say that our whole universe could have been made of the antiparticles of the particles that we see in our universe, right? So you could have an anti-electron, which is a positron, an anti-proton, and so you could run into an anti-Taylor, right? And it would be Taylor, but instead of being made of protons and electrons, it'd be made of antiprotons and anti-electrons. But anti-Taylor better stay far away from Taylor, because if they met, boom, right? They would just annihilate one another, right? And they would both immediately cease to exist in a huge nuclear explosion. So, so we don't have a lot of antimatter around, but we do have some, right? And the antimatter that we do have around comes primarily from nuclear decay. Okay. So these are the different kinds of nuclear decay, and we'll go through each of these. I think we might not have enough time today to finish all of this, but I think we can. Alpha decay, beta decay, gamma decay, positron emission, and electron capture. Okay, so those are the 5 modes of radioactivity. All right, but let's just take them one at a time. Okay, so let's start with alpha decay. So in alpha decay, what you have is an unstable nucleus, right? That then emits an alpha particle, which remember is 2 protons and 2 neutrons, all right? Jumps out. And of course, that leaves a lighter nucleus, right? A different nucleus than the original one, all right? We symbolize these decays with what is called a nuclear equation. So a nuclear equation is to nuclear chemistry what a chemical equation is to normal chemistry, okay? It describes these processes, right? So for example, here is a nuclear equation for an alpha decay. Or alpha radiation. Okay, you have uranium nucleus, right? It gives off an alpha particle, which has this symbol, right? And remember, in a chemical equation, right, we got to balance the number of each type of atom on each side. In a nuclear equation, we have to balance the number of nuclear particles on each side. So the sum of the mass numbers have to add up on both sides, and the sum of the atomic number, the atomic numbers are these, and the mass numbers are these. These have to add up, and these have to add up on both sides, right? So in other words, if this is 92 and this is 2, then we need one other particle here that has an atomic number of 90, right? And if this is 238 and this is 4, then we need another particle here that has a mass number of 234, all right? And if we look on the periodic table, right, the element with a mass number of, atomic number of 90 is thorium. Okay, so this is a nuclear equation, right, describing alpha decay, right? Notice what happens. Uranium nucleus gives off an alpha particle, right, and it becomes something else. Okay. Notice that the sum of the atomic numbers here, 90 plus 2 equals the atomic number here, and the sum of the mass numbers, 234 plus 4, equals the sum of the mass numbers on this side, 238. Okay, so that must be true in every nuclear equation that we write. Okay. So here's an example, another example of alpha decay. Let's write an equation for the alpha decay of polonium-216. All right, so we go polonium 216, right? And if we look up polonium on the periodic table, we see it's right here, right? So its atomic number is 84. So we start with that. And then if it's going to be an alpha decay, then we know it's going to give off an alpha particle, right? So what is the atomic number of what is called the daughter nuclide?
80.
80?
Oh, 82 on the
82.
bottom.
82, right? 82. So we can go to the periodic table and we can see that 82 is lead, right? So this is lead, 82. Okay. And then what must be the mass number of this daughter nuclide?
112.
212.
212, right? So it's lead 212. Does that make sense? Okay, good. Good. Oh, I see. Taylor, you have a question?
Yeah. Why is it helium? Like, could it be something else or?
Well, only because helium has helium-4 has 2 protons and 2 neutrons.
Okay.
So an alpha particle is the same thing as a helium nucleus.
Okay, I see that now. So by definition, the alpha particle is a helium nucleus. It's not like it could release neon.
Right.
Or no.
No. An alpha particle is a helium nucleus.
Okay.
So alpha is always going to be helium-24.
Okay. I was just curious why it was always helium, but okay, because that's an alpha particle.
Yeah.
Okay.
In a nuclear reaction like this, this is called the parent nuclide. Nuclide is just what the term that's used in sort of nuclear chemistry for a nucleus. Okay, it's really the same as a nucleus. So these are the parent nuclides, right? And then these are the daughter nuclides, right? Okay, let's see if you're getting this. Why don't you try this one?
Oh, are these processes spontaneous?
Great question. In the case of uranium-238, yes. So you might ask, well, why is there uranium-238 around if it's decaying? Well, it turns out, we'll get to that a little bit later, but the kinetics of the decay are very slow. So when our solar system was formed, right, we formed the big fusion that was happening formed a certain amount of uranium-238, and all that uranium-238 is slowly decaying away with a half-life that's about 1 billion years. But we'll get to that. But yes, it is spontaneous. Great question. Okay, try to put an answer in the next few seconds. Okay, the right answer was D, and look at that. Virtually all of you got that, so nice work. Way to go. So the way you do that is you just write, for those of you that missed it, bismuth, right, is atomic number 83. 209, right? Because it says bismuth 209. And you just write down the alpha particle, right? And by doing the arithmetic, you can find that that's the daughter. Okay. So again, 205 plus 4 is 209. 81 plus 2 is 83. All right. Very good. What else? All right. So there's some other modes of decay. Now, again, these decays happen in nuclei that are unstable. All right. So most of the nuclei out there that are all around us are stable, but there are some that are not, okay, for various reasons. And those will undergo radioactive decay, right? So for example, there's probably uranium in the ground underneath where you're sitting right now, right? That is uranium-238 and it's undergoing alpha decay, right? So there's probably a little bit of alpha decay going on beneath our feet right now, right? In the ground. And actually Santa Barbara has some shelves, which actually some deposits of uranium. And so, so that happens. All right. So that's a natural thing. Beta decay happens when a particle, when an unstable nucleus gives off an electron. And now you might be thinking, wait a minute, Professor Tro, nuclei do not contain electrons, right? So isn't that weird? So that's one of the quirks of nuclear physics, is that you can have a neutron turn into a proton, okay? And in so doing, it gives off an electron. So notice the charge is conserved, okay? The charge over here is 0. So maybe one way to think about it is a neutron is really a proton plus an electron stuck together. That's not really true. A neutron is actually 3 quarks. And depending on how the spins of the quarks are oriented, it's either a proton or a neutron. So it's really a matter of a spin flip on a quark. I'm not a nuclear physicist, so I don't completely understand it. But as a chemist, I think, okay, I have a neutron and it gives off an electron, but in order to conserve charge, it has to turn into a proton to do that. Okay. I know you're asking me how it becomes a proton. Again, it's the spin flip of a quark, which don't totally understand. But anyway, that's what happens. All right, so let's do an example. Let's say we have the beta decay of Pa233. So this is now beta decay. So we have Pa233. So Pa, we look in the periodic table and we find that Pa is element number 91 right here. Okay. So that's 91 and it's 233. So we put a 233 up there, right? And then it gives off a beta particle. Symbol for a beta particle is, remember, the beta particle is just an electron. Okay, so -1 E0, -1 E0, right? And now if we just play the same game where the numbers got to add up on the left and the right, right? We can figure out what the daughter nuclide is, right? What would be the atomic number for the daughter here?
90.
92? Or
It'd have to be 92, right? Because 92 minus 1 is 91. Okay, so they got to sum and you got to include the sign. And then what's the mass number?
0.
Not 0.
No,
233.
232.
233. Because this is 0, right? So in order for them to add up on both sides, this has to be 233. All right. So then we look up element number 92 and we find that it's an isotope of uranium.
Oh.
Okay. So when palladium, when Pa gives off a beta particle, right, it turns into an isotope of uranium. Good. Does that make sense? Sort of.
So, sorry.
Yeah. Go ahead.
Sorry, just one. So beta does not change the mass of the atom.
Correct. Correct.
Where
Notice what it
alpha-
does. It beta decay. Notice what it does. It changes a neutron into a proton, right? So one of these neutrons. So the mass number stays the same because that's the sum of neutrons and protons, but you get one extra proton, which changes the atomic number and therefore changes the identity of the element. Okay, gamma emission is just the emission of a energetic particle. This actually is a photon. And so gamma emission is often associated with other kinds of emission. So for example, here we said that uranium gave off a alpha particle, right, to form this thorium, okay? When that happens, when any kind of these processes happen, a lot of times the nucleus is left with extra energy, all right? And that extra energy has to be given off somehow. And one way it can give off that extra energy is by giving off a high energy photon, all right? So for example, we could write, there is a particular element called technetium 4399, and we put an M here. That M means metastable, which means it can last in this unstable state for actually a fairly long period of time, right? But it decays to form the same element plus a gamma particle, gamma 00. We write gamma 00 like this because it has no mass and it has no charge. It's a photon. So remember last semester when we talked about the electromagnetic spectrum, and we talked about the different parts of the electromagnetic spectrum, including visible light, ultraviolet light, X-rays, and then gamma rays. Gamma rays were the most energetic types of light that we talked about. And this is where gamma rays can come from, right? From this kind of process. So again, you have an excited nuclide, a nuclide that has extra energy, and it gives off a high energy photon. That's called a gamma ray. Ryland, do you have a question?
Yeah, real quick, is that an M? That M, is that notating that it's an excited particle?
Yep, that's what that means. Yeah.
Gotcha. And then my actual question was, which of these do we know, or do you know which of these processes is occurring in the like applications of nuclear energy that we were talking about earlier?
Yes, we'll get to those. Fusion and fission. So we'll get to those we'll get to those nuclear equations. We probably won't get to them today, but we'll get to them next time.
Got it.
Yeah. Good. Then we have positron emission is another mode. So beta emission is often called beta minus. Positron emission is often called beta plus, right? The only difference, it's sort of the mirror image of beta emission. In beta emission, you give off an electron. In positron emission, you give off a positron. In beta emission, a neutron turns into a proton. In positron emission, a proton turns into a neutron. Okay, so it's kind of like the mirror image of that. Here's an example. Write a nuclear equation for the positron emission of potassium 40. Okay, well, again, we look at the periodic table. Potassium is atomic number 19, so that's 1940. We know the symbol for a positron is +10E. Right, so we do the same thing again, right? And the daughter here has a mass number of what?
18.
40,
Oh, the
right?
mass number.
40 because this is 0. And what's the atomic number?
18.
18, right? So you go back to the periodic table and you can find that 18 is argon, right? So there is the positron emission.
Hey, Tro, what determines like what kind of emission is going to happen?
That's a great question. And so different nuclei are unstable in different ways. So for example, one of the things that determines the stability of the nucleus is the ratio of protons to neutrons. There are certain ratios that are more stable than others. So if the ratio is wrong, then it can either undergo, for example, beta plus or beta minus to adjust the ratio so it's more stable. That's one example. And we'll talk about that a little bit more next time because we're running out of time today. Okay, let's see if you can answer this question. If you're having trouble with this, you could basically write the equation. Okay, sodium 22 is here, turns into neon 22. So what's the missing particle? All right, very good. Try to answer in the next couple seconds. All right, the right answer was B, and voila, most of you got B, so nice work. The way you do that is you go, okay, what has to be, what are the numbers that have to be here in order to balance this nuclear equation, right? So this is 11, so this is going to have to be +1, 22 and 22, 0. So then you know that this is a positron, right? Okay. All right, one last form of radioactive decay, and this one's a little bit different. Instead of giving up a particle, this nucleus actually eats one of its own electrons. Okay, and that's called electron capture. So again, this unstable nucleus captures one of its electrons, and so, for example, we have something like ruthenium 9244, right? And now the particle that it captures is here. It's on the left side of the equation, right? Because it captures it. And then again, we just do the math to figure out what the daughter is, right? So 44 minus 1 is 43. This doesn't change, right? An element number 43 is TC, right? So notice again that in this case, when the electron is eaten up by the nucleus, what happens? A proton turns into a neutron, right? So kind of the same result that we have with positron emission, a proton turns into a neutron. That can all, the same result can happen from electron capture. A proton turns into a neutron. Okay, the end result is the same in both those processes. Okay. All right, so I see we're all out of time. So we'll review next time, but I think you have enough under your belt to finish the problem set, right? Because the problem set is mostly electrochemistry, and then it also has writing some of these nuclear equations, okay? Okay, I'm gonna, because we're completely out of time, I'm gonna end class here, but then of course I'll hang around and answer any questions. Thank you so much, everyone. Have a great afternoon.